Had significant issues during linear this morning, so we'll see if this works or not. Kept kicking me off of Zoom. Any questions at all? I have gone to not lecturing with them today, with them for the rest of the semester. We only had a couple of sections left, so I just posted lectures for them, and they have a quiz due today anyway. So, no, I did not have trig today. Short answer. Questions about anything at all? Chip, from the video, is that what you're talking about? Yeah. Yep, that's the plan. I'm gonna do. Got a couple more examples to do today. Michael tells me he didn't see a video posted on YouTube. Should have said should be titled Cramer-Rao inequality. Is that you able? Others were able to find it? Yes. Yeah. Okay. Okay, that's weird. I'll have to go check on that. Thank you. That's bizarre. Okay, well, we're going to do more of those examples. Got another chat, sorry. I wouldn't go as far to say that, Michael, but I appreciate you letting me know that you'll watch it later. All right. Sorry, the rest of you are getting half of a conversation. I apologize. All right. Anyway, so this problem that I have up on the screen is basically a review of different things that we've talked about. Then we're going to do a couple of problems where we're going to talk about actually trying to minimize the variance of estimators. And then we'll get into the stuff with the Cramer-Rao inequality and seeing some problems about how that pops up. So, all right. So in this particular example, we have that we've got a random variable, tells you what the true value of the parameter is, and it gives a couple of estimators of that parameter based on samples or based on statistics from samples that you gather. And then it gives you three conditions and it asks which of those conditions are true. So the first one's asking whether or not the alpha 1 is unbiased. So what do we think about that? Let's see, we have the expected value of alpha 1 here is 2.05, and the true value of alpha is 2. So in this case, no, this is false. And the reason, again, is because the expected value of alpha 1 is not equal to what the actual value for alpha is. So remember, again, to be unbiased, the expected value of the estimator has to turn out to be what the population parameter is that you're trying to find. So the second one asks if alpha 2 is an efficient estimator. So for our purposes, we know that an estimator, I'll just write this off to the side, an estimator is efficient if its variance is as small as possible. And that's going to lead us into talking about Cramer-Rao inequality stuff later on. But in this particular case, we notice that the variance of alpha 2 is 1.05, and we have another estimator with the same expected value that has a smaller variance. So this one is also false, and this is because the expected value of alpha 1 and alpha 2 are the same. So I can actually compare them. If their expected values aren't the same, it's hard to compare efficiencies, because if one of them's closer to the other, from a relative standpoint, it might be more efficient to use that one even if it had a greater variance, because on average it should be closer to the true value. So we only talk about relative efficiency if we end up with the same expected value for the estimators. So in this case, we have the same expected values, but the variance of alpha 1 is actually less than the variance of alpha 2. So alpha 2 can't be an efficient estimator because its variance is bigger than another estimator's. Now for the third one, this is literally the definition of being consistent. The probability that the alpha 1 minus alpha is greater than any epsilon that we choose approaches 0 as epsilon goes to infinity. So again, the idea behind being consistent is the probability that the parameter value is far away from the alpha value gets small as n goes to infinity. So this is true. Alpha 1 is a consistent estimator. So I put this particular one in here at this point because I just want to kind of, well, I didn't know I was going to get it to start today, but it worked out pretty well that it started off class today. But it reviewed a good number of those different terms that we talked about, with being biased, with being efficient, with being consistent. So any questions about those definitions at all before we start talking about working with some of the minimum variance stuff? Sure. Okay, so to be consistent, the idea is that the whole idea behind being able to take larger samples to give you better estimates, give you better estimates. I mean, that's the kind of the point. So in order to be consistent, what this says is that the bigger the sample, the less your chance should be that your statistic is far away from your true value. So this epsilon value here, that epsilon value is this idea of a measure of being far away. So the probability that the difference between these two things is large, even if epsilon is quote unquote small. We want this idea that we don't want it to be very likely that the statistic that we're computing to give us the estimate gives us an estimate that's far away from the alpha. We want the chances of that happening to be small. So the idea behind being consistent is that if you take larger and larger samples, it should make that probability go down. The larger the sample, the more likely it is that we should have an estimator that's close to the true value. Does that help make it a little more sense? Okay. Yep, you're welcome. Okay. So let's see if we can do a couple of these finding minimum variance problems before we get into some of the Cramer-Rao stuff. So we have in this particular one, we have two unbiased estimates for some parameter. And we know that the variance of the first one is 4 times that of the second. So now we want a new unbiased estimator for the parameter. So it asks what value of the K1 minimizes that variance. Okay, so the first thing that we know, it says we're going to create a new unbiased estimator. So I know that when I do the expected value of this K1 Y1 plus the K2 Y2, I have to get the same thing as the population parameter, whatever that population parameter happens to be. So In this case, let's just call it, for lack of a better letter, let's just call it theta. It's not going to matter what I call it because it's going to go away here in a second. Okay. So we know that expected value distributes over sums and constants pull out in front. So this I can rewrite as expected value, or sorry, k times expected value of y1, or k1 times expected value of y1, plus k2 times expected value of y2 is theta, whatever that theta happens to be. Now we're told that y1 and y2 are unbiased estimates as well. So for expected value of y1 and for expected value of y2, we can plug in theta. And this is why I said it would go away, because if I divide both sides by theta, I get k1 plus k2 is equal to 1. Which kind of makes sense, right? What this particular new estimator is doing is essentially a weighted average, if you will, of the y1 and y2. But you want to make sure that the value that you get out of this is not biased. It's unbiased for the same parameter. So when I do the weighted average, I want to make sure that my weights add up to 1. So it's not a huge surprise that that's what came out of this. All right. We're going to use this basically to solve for the k2 in terms of k1. And the reason why I'm doing that here is because the problem explicitly says what value of k1 minimizes the variance of the new estimate. So I don't want to use both the k1 and the k2 in the problem. I want to actually use just the k1. All right, so now we play with the variance. Because this is the function that I want to minimize. Okay, so we're going to do a similar idea that what we just did with the expected value. Let's break this apart first. I know that the variance will break apart over the sum, and that I do not have to worry about covariance because it says we have two independent estimates. And then when we pull the constants out in front, and I didn't pull the constant out in front. When we pull the constant out in front, we know that we square it. So I can rewrite that as k1 squared times the variance of y1 plus k2 squared times the variance of y2. And now let's start plugging in some things that we know. All right, the first thing that I know is that my k2 is 1 minus k1. The second thing that I know is that the variance of y1 is 4 times that for the variance of y2. So I might as well write this as 4 times variance of y2 here, and just keep this one as variance of y2. All right, so now we want to minimize this thing. So when we minimize, we want to take the derivative. One of the things that we notice, though, is that this variance of y2 appears in both of the numbers, both of the terms, I mean, and it's just going to be a constant. The variance of y2 isn't going to be changing from sample to sample. The y2 is a random variable. It has the same variance. So really, if I think about I'm going to take the derivative and set it equal to 0, that constant is just going to float along as I go. I don't really even need to consider it because it's not going to affect the minimum value of the variance. I'm sorry, the minimum value for the k1. Try one more time. It's not going to affect the value of the k1 that minimizes the variance because this is just a constant multiple times the function. So the input's not going to change. The minimum value will, but the actual input, if you think about the k1 as being the input, doesn't change. So what I'm saying with all of that is that if I think about a function k1 being 4k1 squared plus 1 minus k1 quantity squared, this is the function we want to minimize. And the reason why I'm dropping off the variance piece is, again, because they're just constants. So it's not going to affect where the minimum occurs. So might as well just do the derivative here. Get 8k1 minus 2 times 1 minus k1. Using chain rule on that second one. So that gives me what? 10k1 minus 2? So then if I set this equal to 0, because we're trying to minimize, if I set it equal to 0, we'll get k is 1/5. Now the problem tells us that we're minimizing, so we can probably assume that this is the value that minimizes. However, there's a couple of ways you could check it. You could take the second derivative here and notice that the second derivative will be positive, or you can also notice that if you were to multiply this out, you would get a quadratic that's a parabola that would be opening up. So the vertex would give you the minimum, and because it's giving you the minimum because it's opening up. Questions on that one at all? I think I got one more down here, or does that? Yeah, I got one more here. So let's do this one before we go into the Cramer-Rao stuff. All right. So they are giving you a couple of instruments that measure some distance. They're telling you that the measurements that the different instruments give you are independent. They are telling you that one of them, if m is the true distance, one of them is a biased estimator because it's not turning out to be the true distance, but its variance is less. It's got a smaller variance. And the other one is an unbiased estimator, but of course, since I said the first one had a smaller variance, this one, the second one, obviously has a larger variance. But we want to do the same kind of thing that we just did in the previous problem. We want to try to figure out a value for alpha that makes this new statistic, based on just the x and the y, find a value for the alpha that minimizes the variance. And again, the reason why we care about minimizing the variance is because we're trying to make sure that our estimator that we're using is close to the true value. Well, the larger the variance, the larger on the more likely it is that you're going to be farther away from the true value. So you want a smaller variance so that if you're doing a sample, the value that you get isn't very likely to be far away from the value that you're trying to compute. All right, so let's do the same kind of thing that we did before. The first thing that we notice is it's telling us that we want Z to be an unbiased estimator. So for it to be an unbiased estimator, of course, that means that the expected value of Z needs to turn out to be just M. And then, like we mentioned before, I can split up the expected value of Z, since it's the expected value of the x plus, or excuse me, the alpha x plus the beta y. Split that up. And just like in the previous problem, we can start plugging in things for expected values. It's not quite like the previous problem because one of these parameters, one of these statistics is biased. Oh, for heaven's sake. Yes. Got it. Thank you. So you didn't miss too much. Okay, cool. Just kind of quit. All right. Well, we'll see if it cuts out on me again because I'm getting in the message that my internet connection is unstable. It's not the only thing that's unstable after today. All right. So let's see. For expected value for x, then, it's not quite like the previous problem because in this case, one of our statistics is biased rather than unbiased. Michael's telling me I sound like a robot. So in the first one, the expected value was 0.8 m. And in the second one, though, the expected value is just m because that one was unbiased. However, much like the previous one, we notice that the m will divide out on both sides. And then, since we're trying to find the value of alpha that minimizes the variance, we can go ahead and solve for beta. So we should get 1 minus 0.8 alpha at that point. So then when we're considering the variance, just like before, they tell us that both of the variables are independent. So I can split up the variance with no need to worry about covariance. And then we can pop the constants out in front by squaring them. That is an ugly looking variance of y. Erase that. And then we know the variance of x, in this case, is m squared. We know that beta is 1 minus 0.8 alpha. And we know the variance of y is 1.5 m squared. Okay, so now we want to minimize this function with respect to alpha, but again, we notice, just like in the previous thing, what I was mentioning, this m squared here that's in both terms is just a constant. Now it affects what the output would be, but it's not going to affect where the input gives you the minimum. Again, thinking about it in terms of a parabola, if you multiply the parabola by a constant, it's going to stretch or smash the parabola graphically, but it doesn't change left or right where the vertex is. So I don't really need that m squared in there when I'm trying to minimize this function. So if I think about my f of alpha being alpha squared plus 1.5 times 1 minus 0.8 alpha quantity squared, this is the function that I can find the minimum of. So let's see, we'll get 2 alpha, and then I'm going to get a 3 times a 0.8, so we get a minus 2.4 alpha here, and then a plus 1.5. If I did my arithmetic correctly, because I'll bring the 2 down and get a 3, and then 3 times 0.8 should be 2.4. Oh, no. Sorry, this is a 3. I forgot, I took the 2 times the 1.5. My apologies. And then again, we need to set that equal to 0. So this will give me 3 is equal to 0.4 alpha. 0.4 is the same thing as 2/5, so I will be multiplying both sides by 5 halves, so we get 15 halves in that case. Is this okay with everybody? Good? Okay. Good. I'm just glad everybody can still hear me. I'm going to consider that a win. All right. So we've talked about these couple of problems that talk about finding an estimator that gives us a minimum variance. But notice it's very, very specialized with two specific estimators that we already have. We're doing this from a linear algebra perspective. You're doing a linear combination of those two particular estimates to get a new one. It's a very, very specific type of problem. So what we're gunning for as we go along here are other ways to try to get to minimum variance estimators that don't involve doing that kind of calculus idea. So one of those ways to do that is to work with what's referred to as the Cramer-Rao or the Rao-Cramer, depending on the book you use, inequality. So what it says that if you've got theta hat is an unbiased estimator, then you know that the variance of the theta hat, no matter what the estimator is always going to be greater than or equal to 1 over, I'm going to refer to it as that I of theta, so that I don't have to write that big thing in the denominator. So your I of theta is going to be negative n times the expected value of the second partial with respect to theta of the log of the PDF. It's a lot of words, I know. It's also, it turns out, and this is one of the cooler things that I liked about actually going through the proof in the video, was the fact that this expected value turns out to be the same thing as, or the negative of the expected value turns out to be the same thing as the partial of the log of the PDF squared. So as expected values, those things turn out to be the same. Ordinarily, we'll use the second one to compute this because it's probably a little easier to work with if you just take a derivative and then take another derivative than it is to take a derivative and then have to square out that thing and then look at the expected values. All right, so this I of theta is referred to as the Fisher information. All right, so what this says is that no matter what estimator we have, we can find a lower bound for what all estimators could possibly have for their variances. So whatever the Fisher information is for theta, that gives me a way to figure out what the minimum possible variance is, no matter what the estimator is. Okay, so that's what this inequality is giving us, and that's what this lower bound is telling us. So this lower bound is, just to write this off to the side, this 1 over I of theta is the smallest variance that any estimator can have. I should say any estimator of theta can have. Now, I'm overstating this because if you remember in the video, assuming you watched the video, if you remember in the video, there had to be a couple of conditions that had to be met by the individual pieces. For one, we wanted to make sure that the support of the variable didn't have any thetas in it. So for example, that distribution that we have that's uniform on zero to theta. Sorry, Michael. was what was uniform on 0 to theta. So this would have a support is not free of theta because the support here is that interval from 0 to theta. It depends on what the theta is. So this Cramer-Rao inequality bound that we have doesn't work for this one. It might still work depending on the situation. The issue is, though, the way we did the proof in the video, I talked about being able to move the derivative inside and outside of the integral. If you imagine that the support depended, remember when you did problems back in Calc 2 and Calc 3, where you did double integral problems or triple integral problems, where you had maybe an x as one of your limits of integration? Well, even if you were integrating with respect to y, you knew that that x, as far as that was concerned, it was a constant as far as the y was concerned, but I wasn't able to pull things all the way outside of the integral because that x wasn't a constant in terms of the next integral. So you have to be careful with things like that when you've got the variables up in those limits of integration. So the reason why the proof that I went through in the video worked was because I was able to interchange the derivative symbol and the integral symbols, because I didn't have to worry about that derivative symbol hitting a theta as one of the limits of integration. They were all independent of what the theta was. So at any given stage, I could flip the derivative symbol through the integral, and it didn't change anything. That's why that support being free of theta was important in that case. So when I make the whole idea behind that, that was a lot of words, I know, but the whole idea behind that is when I make this statement at the end, and in particular this word any, I'm overstating a bit. Now, for every problem that you're going to do for these problems, my statement is true. You're not going to do anything that's weird. Everything that you're going to do is going to have supports that are free of the parameter that you're trying to estimate. So, but I did want to make a point to say that, okay, this doesn't work in every single case. It just works in most of the cases that you're going to deal with. All right, so the whole point of doing this is that if you can find your estimator theta hat that actually has a variance equal to this lower bound, then you know it's a minimum variance unbiased estimator. Assuming it was unbiased to start with, of course. But if you know, or sorry, if you find this theta has that smallest possible variance, then it has to be a minimum variance unbiased estimator. That's the only thing that you can possibly have in that case. So that's one of the reasons why we want to use this particular lower bound, is that we'll find this theta, and we'll see that it has a variance that's equal to that Cramer-Rao lower bound, and then we can conclude that it's a minimum variance unbiased estimator. All right, so I got kicked off again. All right. What was the last thing you heard again? Okay, thank you. So if I can find this theta hat and I know that its variance is equal to the Cramer-Rao lower bound, then I know I have found a minimum variance unbiased estimator. So those are the kind of things that we want, because we want it unbiased. We'd like the value that we're getting to be on average equal to the parameter value. And the minimum variance part is the part that well, it's not a guarantee, but it helps us keep our estimates close to the true parameter value. The smaller the variance, the less the estimate can be left or right, if you think about it in terms of a number line. The less of a chance it's too far to the left or too far to the right of the true value. All right, so let's see if we can go through an example. And we're going to do a few examples, and I'll probably go through an example on Friday as well with this. So we've got a distribution, and we want to express the, well, and so like I mentioned that some books flip it around. This one says Rao Cramer. It doesn't matter. It's the same two people. So the Cramer-Rao lower bound for an unbiased estimator for alpha. Okay, so the first thing we need to do, the first thing we need to notice here actually is that they gave us a cumulative distribution function in this case. They gave us the capital F of x as well. So if I look back over here, when I do the Fisher information, that's what we need to figure out first. I need the log of the PDF. So the first thing we're going to have to do in this particular case is find our PDF, which in this case will be alpha over x to the alpha plus 1. Because I get minus alpha minus 1, so I get over x to the alpha plus 1. Now we want to take its log. So when we take the log here, we get the log of the top, and then minus, and I can bring the exponent down and have the log of x. All right, so I know I've got an alpha here. The Fisher information we stated over here was in terms of a theta, but theta is just the parameter we're trying to estimate. So in this particular example, it's the alpha that we're trying to estimate. So we'll do the partial with respect to alpha of this function. So we get 1 over alpha minus log x in this case. And then I need to take the second derivative. Oops. Got to take the second derivative of something here. And we get negative 1 over alpha squared. Now, in this case, we don't have any x's in here. So the expected value is going to be pretty straightforward. Because again, for the Fisher information, I need the expected value of this. But notice that all of our x's went away for this particular one before we even got to the expected value. Now, as a rule of thumb here, when you get to this point, you should be seeing a negative out in front. The reason for that is because notice that in your Fisher information, there's a negative out in front of this thing. You want those negatives to go away, essentially. Because, again, we're trying to find a lower bound for the variance. Variance is always positive. So, saying that the variance is greater than a negative number is a dumb statement because the variance is always greater than a negative number. So when you're doing this expected value piece, you should always be getting a negative so that the negative will cancel when you actually calculate the Fisher information. All right, so your I of alpha here, oops, don't really want to be in red. Your I of alpha here will be negative n over alpha squared. So what this tells us is that the variance of any estimator for alpha, so I'll write it as alpha hat, will have to be greater than or equal to the alpha squared. Oops, it's not negative in front, sorry. The negatives got canceled. I just went through a big thing of talking about how the negatives cancel, and then I wrote it. It'll be the alpha squared over n in this case. So this is your Cramer-Rao lower bound in this case. Any questions on any of that so far? I mean, we're going to do more examples, but this one in particular. This one here? That one where I put the yellow. Okay, so this part here is this. Okay, so that capital F of x is your CDF, and I need to get to the PDF. This always has to be your PDF here. So I had to take the derivative. So I would bring the negative alpha down in front. I would have alpha to the x to the negative alpha minus 1. And so I just pulled out the minus sign in the exponent and brought it down in front. I brought it down to the denominator. Did that help? Okay. That's where that came from. I just did it all at once. Any other questions on that? Why did my fraction? Oh, that's because that's the formula here. That's this part. So we found the Fisher information here, and it says do the reciprocal. To find the lower bound, you do the reciprocal of the Fisher information. That's why I flipped it. Yep, that'll do it. Other questions? Before I do another one? Let's do another one then. All right. So this one has an old friend, our Poisson distribution. So it asks us to calculate the Fisher information for a very specific idea here. So they actually give you the value of the parameter and they give you the sample size, the n. So that's what the n is representing up there above, by the way, is the sample size. So let's go through this. Our PDF for I'm going to do this without putting a 3 in, obviously, to start with here, and then we'll go back through and put in the 3. Okay, so here is your Poisson PDF. And it's not really a big deal if you put the semicolon and then your lambda. The whole idea behind that is just emphasizing the fact that the parameter of interest is lambda, and really the point of the problem is to focus on the lambda rather than the x. Every other problem that we've done before trying to do this parameter estimation stuff is putting in things for x. Now we're trying to figure out something about the lambda. So the whole thing about the notation is literally just focusing your mind on, oh, we're trying to do something with the lambdas rather than the x's. It's more along the lines of, you're given the x's, can you figure out the lambdas? All right, so then again, the first thing you do is take the log of the PDF. So when we take the log, I'll take the log of the first part, we'll have an x and a natural log of lambda. The second part will just have a minus lambda. And the third part will have a minus natural log of x factorial. And in my mind, that natural log of x factorial looks like the ugliest thing, but doesn't matter because it's going to go away here in a second. Because the next step is to take the derivative with respect to the parameter. Now, like I said, that natural log of x factorial part doesn't have the parameter in it, so it's just going to go away. So took the first derivative, we should get x over lambda minus a 1. Take the second derivative, and get negative x over lambda squared. Next step, take the expected value. Now this one does have an x in it. So I can still pop out the constant, but I still have to worry about expected value of x here. That x is not a constant, that's depending on the sample. So I still have to compute this expected value of x. Depending on the problem, either you know the expected value based on how what the distribution is, which is the case here because it's a Poisson, or you may have to go through and do an integral. I mean, it just may be the case that that's not a commonly known distribution, so you'll actually just have to go through and grind through the expected value of the function. But like I said, this one, we know. It's a Poisson distribution, so its expected value is lambda. So we get negative 1 over lambda. So now when we do our Fisher information, that's negative n over lambda, because we take the expected value and multiply it by, it's not negative n, it's positive n. We take our expected value and multiply it by negative n. So then this tells us that the variance of any estimator for lambda is always going to be greater than or equal to lambda over n. We reciprocated that point. Now, for this particular problem, they said figure out what the Fisher information was, which is this piece over here, right? They actually said find the Fisher information. I just went through and did the Cramer-Rao lower bound. But for the Fisher information, it said if n is 25 and lambda is 3, so then your Fisher information would just be 25 over 3 in that case. So just to finish this off for today, and we'll do some more examples next time. One of the things that we did before was that the maximum likelihood estimator for lambda, we did this back when we talked about maximum likelihood estimators. The maximum likelihood estimator for lambda is the sample mean, right? Well, we know that the variance of the sample mean is the variance of, for heaven's sake. One minute. It literally could not wait 1 minute to cut out on me. Literally 1 minute. Okay. So back to this again. We know that the maximum likelihood estimator for lambda is the sample mean. And we know how to calculate the variance of sample means. It's the variance of the distribution, which in this case, since it's Poisson, is lambda over the sample size. So notice that your maximum likelihood estimator here hits that Cramer-Rao lower bound. So what that tells us is that your maximum likelihood estimator, x bar, is a minimum variance unbiased estimator for lambda. Because the variance for your maximum likelihood estimator, or the sample mean, has the smallest possible variance. Questions on that at all? Everybody still hear me? Okay, good. All right, so we'll do more of these examples. I forgot that I hadn't sent out these sample problems well ahead of class. I sent them right before class, so we'll do more of these on Friday. Hopefully, hoping that the Zoom doesn't kill itself 8 or 10 times during class. So, anyway, until then, I will talk to you all later. All right, bye.